Hello, this is Margarita Perez Gonzalez, and I would be showing you how to make electron dot diagrams for chemical compounds. As you know, we have seen how to make electron dot diagrams for elements. It is our time for we to learn how to do them for compounds. Okay? So this procedure was proposed by Professor Castellanos in his book on 1999, and this is going to show us a procedure on how to do these structures for compounds. Okay? As you know, this is a model, and models are there to explain reality. Okay, so we're there to remember that this is not something that would be working for every compound, but it would work for most compounds. And we're there also to remember that this procedure works for those compounds that have covalent bonds. We have seen in class that covalent bonds are those that share electrons, okay? So once you have that type of bonds, you would be able to do this structure, okay? So this procedure consists of a series of 8 steps, and we're there to review first the steps in theory, and then we're there to work an example. Are you ready? Okay, so for we to make compound representations, first thing that you're there to do is that you're there to write electron dot diagrams for every element in the compound. Step number 2 is calculating the number of electrons provided by each atom, and then we have to add them up. So we get to a number of electrons provided, or valence electrons, for all the compound. Step number 3 is for you to calculate the total number of required electrons for each atom. At this point, remember that you need 2 electrons to fill the sublevel 1s that hydrogen has, and you need 8 electrons for the rest of the elements, because, as you remember well, elements would like to get the structure of noble gases gaining 8 electrons on its last shell. Once you do that, we move on into step number 4, and there you calculate the number of electrons involved in bonds. So what you do in here is you're there to subtract the required electrons from the electrons provided. Okay, so that's step number 3 minus step number 2. On step number 5, you're there to calculate the number of bonds. Remember, always every bond involves 2 electrons. So you're there to divide the number of electrons involved in bonds over 2. And that's going to come up, and that's going to give you the number of bonds present in the molecule. And that's something important. On step number 6, you're there to calculate the number of free electrons in the molecule. So the way for you to do that is you're there to subtract the electrons involved in bonds from the electrons provided. So that comes to be step 2 minus step 4. With that, you will know the number of free electrons within the molecule. Step number 7, you want to draw the structure representing the bonds and the free electrons, always in pairs. And finally, step number 8 is for you to calculate the formal charges for every element in the compound. Okay, so once you follow this procedure, you would be able to draw the structure for a compound, for a covalent compound. Lewis dot structure for a covalent compound. Is that right? Are you ready for the example? Okay, so, oh, sorry, I forgot to tell you how to calculate formal charges. Okay, so formal charges would be calculated in the following way. You have the group number, and that's the same as the number of valence electrons, and you subtract that, the number of bonds, minus the number of free electrons. And this is a way for you to calculate the formal charges. Okay, so let's move on into the example. So we're there to see what happens in sulfuric acid. Okay, sulfuric acid has covalent bonds and has a formula of H2SO4. Okay, so step number 1, we want to do the Lewis dot structure for every element. We take hydrogen, and remember hydrogen is a group 1, so it's there to have 1 valence electron. Then we check out for sulfur, and sulfur is on group 6 of the periodic table, therefore it has 6 valence electrons. After that we've got oxygen, and oxygen and sulfur are in the same group, so they should have the same number of valence electrons. Notice in here that's more important how many electrons do you have than exactly where you place them. Okay, so in this case you could place them anywhere where you want, just making sure that there are 6. Okay, so step number 4 is for you to calculate the number of electrons provided by each atom. Okay, so we have hydrogen, but as you know we have 2 hydrogens in the molecule. So 2 hydrogens times 1 electron provided by hydrogens, that makes up to 2 electrons provided by the 2 atoms of hydrogen. Then we check out for sulfur, and in sulfuric acid we only have 1 sulfur, and that sulfur is providing 6 electrons, so sulfur provides 6 electrons. Finally, oxygen has 4 atoms within the structure, so we're there to multiply 4 times 6 because every oxygen provides 6 electrons. So that comes up to a total of 24 electrons provided by oxygen. So if we add these electrons up, we have 24 plus 6 plus 2, that gives us a total of 32 electrons provided. Then we would move on into step number 3, and now we're there to calculate the total number of required electrons for each atom. As you know, this number corresponds to the number of electrons that are needed to fill the last shell. Okay, so we would consider 2 for hydrogen and 8 for the rest. Okay, so for hydrogen we have 2 hydrogens, but every hydrogen requires 2 electrons. So to complete the duet, okay, because it's just requiring 2. So that gives us a total of 4 electrons required for hydrogens. Then we have sulfur, we have 1 sulfur atom, but it needs 8 electrons to complete its shell, so we write 8. And finally we've got oxygen, but we've got 4 oxygen atoms. So we're there to multiply 4 times 8, and that gives us 32. If we add them up, this is 32 plus 8 plus 4, it gives us a total of 44 electrons required. In step number 4, we're there to calculate the number of electrons involved in bonds. So that was step number 3 minus step number 2. If you remember well, we calculated in step number 3 the total of required electrons. So those are 44 required electrons minus 32 electrons provided for the atoms. So we've got a difference there of 12 electrons involved in bonds. Once we have this number, we get to divide these 12 electrons into 2 because we know every bond involves 2 electrons. So that gives us a total of 6 bonds within the molecule. And that's something that we're going to use to draw the structure. Step number 6, we're there to calculate the number of free electrons. So that's the difference between the electrons provided and the electrons in bonds. So this gives us a total of 44 electrons provided by every atom in the molecule minus 24 electrons involved in bonds. Please watch out that at this point we don't write the 12 bonds, but the 24 electrons involved in them. So that gives us a total of 23 electrons. Okay, so we're now ready to draw our structure. Remember, we're there to use 6 bonds and 20 free electrons. So the first thing that we're there to do is we're there to locate the central atom. You would know whenever you've got acids that have oxygen that normally the non-metal stays in the center of the molecule, then the oxygens and then the hydrogens. So that's what we're going to do. Some authors say that also the atom that goes in the center is the one that requires more electrons. So at this point, also following that criteria, sulfur is the one that requires more electrons. So we would place sulfur in the center of the molecule. Is that right? After that, we would locate every oxygen surrounding the sulfur atom. And after that, we only have 2 hydrogens. So we have the hydrogens bonded to the oxygens. Is that right? So that's normally what you do. Then you've got 6 bonds, okay? So first step is for you to place every bond for each 2 atoms, okay? Or in between 2 atoms. Okay, so we've got 4, and then we've got 5, and then we've got 6, sorry. So we know this structure doesn't have double bonds because we have completed the number of bonds that we need. It only has 6 bonds. Okay, so we're now there to locate 20 free electrons. Okay, at this point, remember that in covalent bonds, by sharing, we're there to complete the octet. Okay, so at this point, sulfur has completed its octet because it's sharing with oxygen. So 2, 4, 6, and 8 electrons. So sulfur already has the structure of a noble gas. So we would just leave it there. Then let's look what happens with hydrogen. Hydrogen is completing its duet by sharing these 2 with oxygen, and the same for the other hydrogen. So we don't have free electrons in here. Now, what happens with this oxygen in here? It's sharing 2 and 2, so that gives us a total of 4. So we need a couple of electrons in here and a couple of electrons in here. And in that case, oxygen is now completing its octet. We would do the same with the other oxygen. 2, 4, 6, 6, and 8. So it's all complete. Now, what happens with these 2 oxygens? They only have 2 electrons that are being shared with sulfur. So we need 6 extra electrons. And the same goes for the other oxygen. We need 6 extra free electrons for this oxygen to complete its octet. So if you add all free electrons up, you've got 6 and 6, that's 12, 14, 16, 18, and 20. So we came into a total of 20 free electrons. Is that right? So that's exactly the structure for sulfuric acid. At the end, we're there to calculate the formal charges for every element, starting with sulfur, okay? For you to remember, formal charges are calculated by writing the group number minus the number of bonds minus the number of free electrons, okay? So for sulfur, sulfur is on group 6. In the structure, it has 4 bonds, and it doesn't have any free electrons. So that gives a formal charge of +2 for sulfur, okay? Now, every hydrogen is in the same circumstance, having 1 bond and being on group number 1 and having no free electrons. So the formal charge for every hydrogen is 0, okay? Now, for those oxygens linked to hydrogens, the formal charge would be as follows. Group 6, each of them has 2 bonds and 4 free electrons. So the formal charge for that oxygen is 0. And the same goes for the other oxygen linked to hydrogen. Finally, we've got the two other oxygens that only have one bond and 6 free electrons. So 6 minus 1 minus 6, this gives us a formal charge of -1. The same happens with the other oxygen. So we've got two oxygens with a -1 charge. Now, if you add the charges, +2 -1 -1, that gives you a total charge for the molecule of 0. And most compounds are neutral, so this tells us that we've worked in the correct way. So I hope with this example, this is clear for you and you would be able to practice how to make compound representations for using Lewis diagrams, okay? This is the reference of the book I used is Química Orgánica, and the author is Castellanos. Thank you very much.